In this section, we'll explore some graph theory for the estimation of the spectral radius, particularly for iteration matrices of relaxation methods you studied in the previous section. Let's get started with a definition. A permutation matrix is a square matrix in which each row and each column has one entity of unity, with all others being zero. Let's see this example. Start with an identity matrix. In 3D, we have this identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Now we apply row interchange operations. So first we move this bottom row to the top. Okay, here's an example. And we move down of these two rows. That is a permutation. If you look at rows and columns, then you can see only one entry of unity and all others zero. So it is a permutation matrix. In general, a permutation matrix is obtained by such row interchanging the identity matrix. We have another definition. For a square matrix, it can be complex valued. The reducibility is defined in this way. If there is a permutation matrix P such that this operation, which is called a similarity transformation, makes this matrix. So original matrix is transformed into this form. Okay, let's try to make lines here. So this portion is completely zero. It is related with reordering of a point. In general, in an algebraic system, a row is corresponding to a point, and once you order the points different way, then you will get the matrix in different form. That is exactly the same as along with such similarity transformation for certain permutation matrix. So assume for a given matrix, it is happening. Then once we try to solve, for example, AX equals B, then along with this matrix, we have here X and right inside B. Now, matrix is given in this way, then you may consider parts of X and parts of B. So let's say this is X1, that is X2, and that is B1 and B2. Then when we try to solve this problem, then this bottom portion makes this algebraic equation A22 X2 equal B2. So we can solve this one for X2, and by using X2, now we can decide X1 by solving the top portion. So the system is solved in reduced way. So that's the reason once a given matrix A can be transformed into this form, then we say that the matrix is reducible. Otherwise, it is irreducible. Geometric interpretation of the irreducibility by means of graph theory is quite useful. So let's begin a geometric interpretation of irreducibility. Okay, here we have definition of directed graph. For given matrix, n by n square matrix, and we put n points, just to put points on the plane, and you can put anywhere, whatever you want, and you can put the points, just n points, and we say these points are nodes or nodal points. And once Aij in the entry of as entries, Aij is non-zero, then we try to make an arrow, directed arrow. So for example, Aij is non-zero, then we are making that arrow from Pi to Pj. And this arrow is made when Ai is non-zero, I to I. Right? So in this way, we put the directed arrow for the corresponding points, then it is called direct graph. Look at here this example. Consider this matrix, okay? Now we put here P1, P2, P3. You can put some other way. For example, you have 3 points here, 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 and you may say that is P1, now that is P2, and that is P3. It doesn't matter. Okay, let's try to make a direct graph for this arrangement. Okay, A11 is non-zero, so we have 1 to 1. And A12 is non-zero, so we have that arrow. Now for second row, there is A21, so from 2 to 1, now 2, 2, and 2, 3, non-zero, so we make that one. Now for third row, 32 is non-zero, so we can make an arrow like that, and then 33 like that. Okay, in this way, you can make a direct graph. And P1, P2, P3, then exactly the same way. Now the directed graph is drawn in this figure. Okay, that is the directed graph for this points. Okay. Now we define strongly connectedness. Strong connectedness. A direct graph is strongly connected if for any ordered pair of nodes there is a direct path of a finite length. Of course, we have a finite number of points so that we have only a finite length. And however, anyway, for definition, we are using it here. So that from Pi to Pj, we can connect. For this graph, if we choose P3, P1, then we can go here and like that. Only the way is just once we have arrow, then along with arrow direction you can go. So if we choose again, for example, P1, P3, then from here you can go here and you can go over there. So from any choice of 2 points, now in this direct graph, we can see every points are strongly connected. So the graph is strongly connected. We have a theorem. Of course, we'll see the proof, but you can find the theory from, for example, Vargas' book. He made wonderful contributions to the Society of Numerical Linear Algebra. He's a genius man. He spent his life in Kent State University. Okay. A square matrix A is irreducible if and only if its directed graph is strongly connected. first of all, for this matrix, it is strongly connected so that it is irreducible. Now, I write down over there, this operation, the similarity operation is related with a point reordering. Once you try to name the point different way, then your corresponding algebraic system has a different form. However, that can be written as in this similarity transformation. So this operation is exactly a kind of point reordering. Once the graph is strongly connected, no matter how you try to reorder, how you name the points, it doesn't matter. Strongly connected graph must be always strongly connected. So that once the graph is strongly connected, then you cannot find a transformation such the permutation matrix such that this transformation is a reducible system. So that we can say that on the proof of this theorem is partially geometric. However, anyway, irreducibility is the same as the strong connectivity of the directed graph. Okay. Okay, we'll go to now eigenvalue Locus theorem. First, we define lambda I, capital lambda I, that is, for either of the matrix, for each row, so the ith row here now, and we try to, that is diagonal, we exclude the diagonal entry for remaining entries, we try to add in modulus. First, take absolute value and add them except this main diagonal entry, that is lambda I. We have a theorem. A is a irreducible square matrix. It can be complex valued or it can be real. It doesn't matter. Okay. Now, Gerschgorin theory in 1931 says this one. All eigenvalues of A lie in the union of disks in the complex plane. This disk is made centered at AII and the radius lambda I. So lambda I is addition of the off-diagonal entries in modulus. So each row is making a disk, and union of this disk is the place where eigenvalue can be. That's the theory. Now, when we consider this one, then, okay, for example, let's see here, for this matrix, we have now, that one is lambda 1, this matrix, this is 1, lambda 2, so off-diagonal entry addition, 2, again, lambda 3 is now 1 in modulus, yeah? So that when you try to make the disks, then you can make that way. For this one, the center is always 2. It's 2, A11 is 2, so around the 2, we have a radius 1 circle. And for second one, again, A22 is 2, so around 2, radius 2 circle and inside, so that we have disk of radius 2. And then for last one, okay, it's same as that one anyway. Okay, we have this discus. And union of this discus is definitely Now that one, right? When you make this union of disks, then the boundary is involved. So that once we say eigenvalues are on the inside union of, in the union of this disks, then because this boundary touches 0, so you may ask a question, is it possible for an eigenvalue to be 0? So that is not answered from this theory. Now, Taussky theory, after 17 years later, answered quite clearly for the question. In addition, assume an eigenvalue, lambda, small lambda, is on the boundary of any disk. Any disk, on the boundary of any disk, so that once an eigenvalue is on a circle, okay, for example here, then all circles must pass through the point. So for this example, the boundary points cannot be an eigenvalue of this matrix. So eigenvalues must be always inside. Once it's on the boundary, then the circles should pass this one, but apparently right now the two circles are far away from this point. Right? Okay, that's the Taussky's expansion of Gerschgorin theory. So we say this whole thing, we call this whole thing the Gerschgorin-Taussky theory. Okay. Now, for this metric, let's try to see the spectral radius of iteration matrices for the Jacobi, the Gauss-Seidel, and the SOR. Let's begin with Jacobi. For the metric, n is chosen to be diagonal, and n is m minus a. Now, the iteration metric is m inverse n. So we have that. You can easily see that off-diagonal entries summation is half for the first row, and for the second row, addition is 1. Now, for the third row, addition is now half. Okay, so we can make disks on the plane, in the plane. For every row right now, AI, okay, II, the diagonal entries, it's all the 0. So that for the first row, the circle is in center is 0 and radius half. So we have that. There's half. From second one, again, center 0 and radius 1. We have that, right? There's now 1. And third one, and center 0, radius half, the same. Now, for these three disks, union must be this disk. Now, from Taussky part, we can say that any of the eigenvalues cannot be on the boundary, because once it is eigenvalue, then all circles should pass this point. But it's not happening that way. So boundary points cannot be an eigenvalue of the iteration metric of the Jacobi method. Okay, so we can conclude every eigenvalue must be interior of this disk. So we can say that now the eigenvalue is largest eigenvalue is strictly less than 1, which means that the Jacobi method is convergent. Spectral radius must be strictly less than 1, So the method must be convergent. By using a software, we can see now the spectral radius is 1 over square root of 2. So it is really smaller than 1. Exactly the same way for the Jacobi Gauss-Seidel method. We can test it. Now there's M. Sorry. Now we get the iteration metric. Okay, that is this one. And then here, the lambda 1 is half, lambda 2 is again half, lambda 3 is 1 over 8, and center is 0, 1 quarter, 1 half. So we have now the disk, and now another disk, and another disk. That union, in fact, in the beginning, you have to start with inequality. But if you try to make a picture, then it's not on the boundary. You can easily see that. Okay, let's try to make the circles. And around the 0, half, okay, first. And around the quarter, half, so that now, okay, that is quarter, and then half, so that, and that means here, like this. Same size, but it's moved quarter. So that will become 3 over 4. And then around the half here, 8. So the very smaller circle is given. So union of these disks is definitely here is not touching the circle of radius 1. So we can see easily the real part of any eigenvalue must be larger than minus half and smaller than 4 over 3. So we can say that the spectral radius is strictly less than 3 or 4. It cannot be on the boundary because already the circles are given in this way, so that there is no common point. Okay, so we can conclude through the graph theory in this way. If we compute practically the spectral radius of the iteration metric, then we reach at half. And that one is, okay, let's go back to this one. The spectral radius of Jacobi iteration metric is 1 over square root of 2. So the error reduction rate is around here. So if you do 2 iterations, then its square is 1/2. And that is exactly this value. So in theory, and it's known that Gauss-Seidel iteration is twice faster than the Jacobi iteration. Let's consider now the S1. S1, this is M. And earlier in our test, in the last section, we chose omega 1.2. So we'll use that. So the iteration metric is organized in this way. Now it's a little bit complicated. However, you can check quite easily through a small program. Now, octagonal entries in modulus, you can sum them, and then from the center, you may imagine, and particularly not all circles, and only on x-axis. And you can check the maximum and minimum possible values, and you can check it by using a small program nicely. Then here, you can easily check that now real part of the eigenvalue must be from here to there. So that more or less, this is the right answer, and so we can conclude the spectral radius of S1 iteration metric is bounded by 22 over 25. Because of the complication, it is happening, so that anyway, this analysis guarantees that the S1 is convergent. Now let's check the spectral radius by using a computer program. Then we can see is 1 over 5. So through this graph theory, we can check if the spectral radius of iteration matrix is less than 1. So that's really first step you have to check. If you design an algorithm, first of all, you have to make sure your algorithm converges. This is a simple method to figure it out. Now, let's deal with a little bit of a theory. Positiveness. A metric, square metric, is diagonally dominant if the main diagonal entry for each row, the main diagonal entry in modulus is larger than or equal to lambda I. Already we defined this one, just addition of absolute values of diagonal entries. So the diagonal entry in modulus is not smaller than the summation of other entries in modulus. Then we say diagonally dominant, reasonable name, right? And also we can define irreducibly diagonally dominant. In this case, if a matrix is irreducible and again diagonally dominant. However, once we try to say these two things together, then we require one more. At least one row, we have strictly larger. The diagonal entry is strictly larger than other entry summation. So with a strict inequality, holding at least one I. Okay, let's see example over there. The matrix we exemplified here. That one. Now, okay, for every row, it's at least the summation of diagonal entries. So it is diagonally dominant. And also it is irreducible. So once we try to say this is irreducibly diagonally dominant, then at least one row, the inequality must be strict. But here we have a strict inequality. This 2 is strictly larger than 1. Also another one here, 2 is strictly larger than 1. Okay? So it is irreducibly diagonally dominant matrix. Okay. If a matrix, square matrix is strictly means that, strictly diagonally dominant means that for every row, the inequality is strict inequality. So for every row, the main diagonal entry is strictly larger than the summation of other entries. So then we say strictly diagonally dominant. And either strictly diagonally dominant or irreducibly diagonally dominant. So in any case, it's a diagonal dominant and at least one row, the inequality is strict. Then the matrix is non-singular, and if all diagonal entries of a matrix A are positive real, then the real parts of all eigenvalues are positive. So once this additional condition is given, then all eigenvalues real part is positive, which means that once you consider the complex plane, then eigenvalues are all on the right side, excluding this y-axis, the vertical axis. So in the case, we say that that is your definite metric. Either right side or left side, then that is a definite matrix. Eigenvalues are all positive, then we say, and positive definite. And the reason we consider this theorem is that if your the eigenvalues are partly right side or partly left hand side, then it's much harder to solve. Once it is in one side, then it's easy. If you make a scale and if you try to make some arrangement, then you may, for this case, you may, by scaling, you may put these eigenvalues in certain area. So that if you are trying to use some point, then easily you can design a relaxation method. But once it is the other side, then your relaxation method may not be convergent. So that's the reason such property is very important. Now, here, a Hermitian metric is a complex version of a symmetric metric. So a Hermit metric, then now that condition means that now eigenvalues must be all positive. So eventually we can conclude that here the metric must be positive definite. Okay, now we'll continue some more theory. This portion is not related with your computation. However, it's quite important in engineering applications. The so-called M matrices appear in various engineering applications. For those matrices, the relaxation methods can be employed very effectively. Here, effectiveness means that the convergence and also some efficiency. So you can enjoy very rapid convergence along with the relaxation method. But somehow these are old-fashioned algorithms, so that modern scholars are not well using. So that's the reason I'm trying to say something in this subsection. Okay. For real matrices, in reality, in engineering applications, mostly the matrix is real. Okay. The splitting, A is n minus n, is a regular splitting. If we have these two conditions, of course m must be non-singular, but m inverse is non-negative. Once you consider inverse of m, then all entries are non-negative. For n, again, all entries are non-negative. Then we say this splitting is a regular splitting. Once you start with a regular splitting for relaxation method, then, and also assuming A inverse is non-negative, first of all, A should have this property. Then, now the spectral radius of iteration metric is given in this way. So this quantity, the same quantity and bottom, one is added so that this quantity must be smaller than 1. That means that once given metric has this property, and if you start with regular splitting, then the relaxation algorithm is convergent. It's guaranteed convergence. Okay, now we go here, M metric for a given metric. Now, off-diagonal entries are non-positive, all of them. And also, A inverse is now non-negative. All entries are non-negative. Then we say the metric is on M metric. It looks like requiring quite serious the conditions. However, this one is quite popular. Inverse is non-negative is quite natural, in fact. For example, you consider heat transfer, and you imagine in a classroom there is a heat source. Then, once the heat source increases temperature, then as time goes, the temperature over the whole classroom will increase. So once the physical problem is represented as an algebraic system, then it is given now Ax equals B. That means that the solution X is A inverse B. Now that is the source. Once the source has increased the value, then now solution should have increased the value. The reason is A inverse has non-negative values. Once somewhere it is negative value, then you can choose the source, even though they are increasing, and along with the negative value, you can get the decreasing value. It's physically nonsense. So that's the reason, once your problem is well defined physically, then your algebraic system can be on M matrix. It's natural, physically sound, the application. Okay. So once it is M matrix, then satisfying this one so that you start with regular splitting, then it is always convergent, which means that in various engineering applications, the relaxation method can be employed very effectively. Now, again, this theorem gives the conditions for regular splitting. Once the metric is M metric, and now M is obtained by setting certain off-diagonal entries of A0 as in Gauss-Seidel and Jacobi, then M minus N, this splitting is a regular splitting. So in many applications, Jacobi and Gauss-Seidel are along with regular splitting. Of course, S1 is better than Gauss-Seidel. So all relaxation method you studied in the last section will be convergent. Now, another theorem is saying that now the setting certain off-diagonal entries of A to 0, okay, the manner can be different. In fact, for Jacob method, we set every off-diagonal entries to 0. But for Gauss-Seidel method, we set only a proportion of off-diagonal entries to 0. So that once you try to set more off-diagonal entries, then slower. So that's exactly this one. We have two different splitting. Now, here N2 is larger than N1. Then now spectral radius becomes the corresponding iteration metric split. The spectral radius becomes larger than the smaller case, which means becoming slower. So if you want to keep as much as possible, and now smaller number of double entries change it into 0 for m, then your convergence can be faster. So this theory also explains why the Gauss-Seidel method is faster than the Jacobi iteration. Okay, here this theory is a little bit complicated when you try to prove them. However, here the main point is that in reality, M matrices are quite popular in various engineering applications, and for those systems you can apply the relaxation method very effectively. Okay, this is the end of the section. Thank you.